Okay, so our next topic, I will talk about approximate nearest neighbor search, or kind of applications used in information retrieval. Okay, so I will take this tutorial as a talk is given in CBPR 2023. CBPR is a top conference in computer vision and pattern recognition. Okay, so they give such a talk. It's called a neural search in action. Okay, and they contain 3 topics, and I will take the first one and the second one to use their slides to give you an overview of the nearest neighbor search of the state of the art. Okay, so the first slide is given from Professor Masui. So it's from the University of Tokyo. Okay, so I will give a quick through it. I will not go over all the detail about the slides because I have 2 slides, 2 topics to be given here. So the first slide is just give you a general knowledge, a background about the graph-based search. Okay. So this is mainly from the nearest neighbor search. Okay, we abbreviate as NN search. So in NN search, we have a data set. The data set is you can treat there. Actually, they are a vector. Here is a d-dimensional vector for each x. So I have n data. Each data is a d-dimensional vector. Okay, so such a data set is very, I think it's the main trend, especially in the LLM age. Okay, because all the data, all the tokens are stored in vector form. So you can think it's a vector database. It's not like the traditional database, right? Traditional database is use a table. The table contains many fields, attributes, and you just use some SQL language to find what is the attribute, satisfy your query, like the Boolean vector search. Okay, but in LLM models, all the data are represented as vectors, so we will store all them in our database. Okay, so it's a vector database, and we try to find the nearest neighbors, the most similar items from the data set. Okay, so give a query. The query is, for example, is a 4-dimensional vector here. Then I want to search in our data set, and the data set should return me by using some metrics. Okay, here the matrix is a Euclidean distance. So I will compute the Euclidean distance between the query and each of the data in the data set. Okay, so after it, I can find is the distance, right? And I find the smallest one. After me, try to find the data at least the smallest distance, and I will return the result. For example, x 74. This vector has the smallest Euclidean distance for the query. So this is what the nearest neighbor want to do. Okay, so it's a very simple idea, right? We just find the nearest one from the data set. Okay, so it's a fundamental problem in many computer areas, in machine learning, in information retrieval, in data mining, and computer vision. They are the fundamental technique widely used in many areas. But if you find the nearest neighbors in this way, actually is if you use a linear scale, or we call it a reductive search, to compute all the data in the data set. The complexity will be n times d, nd. Okay, n is the number of your data, and d is the number of dimensions. So the time complexity is big O and D. When the n and the d are very large, the time complexity is very big. Okay, so it means the computation time is large. Okay, you will get a very slow response. So that's why we don't want the exact nearest neighbor search. We want to perform an approximate. Approximate means maybe you will not retrieve the correct answer. You have and maybe have 99% to be correct. Okay, so 1% may be fail, but your search time is faster. Okay, so we call it approximate nearest neighbor search. So the idea is the same. Okay, we want from this data set to find the smallest distance, but we will build some index structure to organize the data in the data set, so that you don't need to perform the exhaustive search. You don't need to perform a linear scan. You just follow the index structure to find some candidates. The candidates just contain a small portion of the data set, maybe just 0.001%. You just scan a few portions, a small fraction of the data set. Okay, so let's make your search faster. But the trade-off is you may not retrieve the exact neighbors. Okay, so we have to try to find a trade-off between your runtime. Okay, should be fast. The accuracy, okay, we hope is high, and the memory consumption. We hope your index structure here is additional storage in your memory. So we hope your index structure should be compact, not to consume too many memory. Okay, so we try to find the trade-off between the three factors. Okay, so in this size, let's suppose your number of data is smaller than 10 to the 9. Okay, so it means less than 1 billion. Okay, so we suppose your data set is about million scale, not billion scale. But the next topic, we will talk about how to handle the billion scale. Okay, here we give some use cases. Okay, so the first case called a multimodal search. Okay, in multimodal search, so you just recall the use case for clip. So remember clip? The clip framework, we can perform the multimodal retrieval. Okay, so here we give image, and we use the clip image encoder. We use this pre-trained model to encode each image into a vector x1, and the next image x2, and until xn, all stored in our vector database. And now I have a query. It's in text. Okay, the two dogs playing in the snow it's a text modality query, and the thrower clip text encoder is also a pre-trained model, and I convert it into a vector. Then I can use the text vector to search in my image vector dataset. Okay, so this is the way to perform a multimodal search. Okay, so with the same concept, you find the smallest distance and return the result. And the result is corresponding image like this. Okay, so in this case, you can think it's successful because it match your text description. Okay, and in this work, okay, your image encoder and the text encoder are determines your upper bound of your system accuracy. The next use case, okay, is related to our term project. Okay, it's called a RAG, retrieval augmented generation. Okay, so let me illustrate the general idea. Okay, so first here we have suppose we have Chih-GPT. Okay, so now it's trained in 2021. So the Chih-GPT doesn't have the knowledge after 2021, right? Because they use the data before the 2021. Okay, so now I have a question that who won the curling gold at the 2022 Winter Olympics? Okay, if you ask this question to Chih-GPT, it will say, I'm sorry, I have this knowledge. Okay, it cannot respond the answer to you. How about another way? It's called with the embedding, use the RAG technique. So I can suppose I have a data set, update data set like from the Wikipedia. Okay, the Wikipedia will update, right? Update every day. You will be update this knowledge in Wikipedia. So you just crawl all the data from Wikipedia. Okay, so you say, okay, so it contains some knowledge related to the 2022 Olympics result. Okay, so you just collect all the documents from the Wikipedia. So you find a source, a data source, later will be updated, repeated, and then you just convert all these documents into vectors stored in your data set. So here, the first document is throw the text encoder to be a XY vector. The second vector and the second document and the nth document. All they are stored in your vector database. Okay, so we can perform the search in this way. Given a query, we use the same text encoder to transform into a vector, a text vector here. And then we use this query to search in our text data set to find the smallest distance document here. Okay, this document say, okay, actually this document give a list of the 2022 Winter Olympics medal winners. So with this information, it's an augmented information. So I can feed this information. Okay, use the below article. When you submit your queries, but now you update with the additional information by using the search result from your data set. Okay, so using the below articles we found from our vector database, and use this information to ask the Chih-GPT again. And then, okay, the Chih-GPT now has a knowledge about the 2022's Winter Olympics. Okay, so now we can give the correct answer to you. Okay, such a technique is called a RAG, or this our term project wants to do. So in our term project, next week our assistant will give you more detailed examples and the codes to you. And I hope you can design your own recommender system so that you can collect the data what you want. For example, you want to collect a movie data set or a computer game data set. You can collect it and update it. You have an updated data set and all transform. Use the technique to store in your data set, okay, so that you can follow this idea and choose any one LLM model you want to combine the whole process by yourself, so that you will have your own personal recommender system. and it's the easiest way to leverage the power of LLM. Okay, the easiest way to provide the knowledge to LLM. You don't need to retrain a new LLM model. You don't need, because we cannot afford the so huge computation. Okay, we can only use the pre-trained model. Yeah, but the pre-trained model, we can provide extra additional knowledge by using such a RAG technique. Okay, so that you can have the updated knowledge here and provide it to your LLM model. Alright, so there are already many related algorithms and the library services for you to, if you want to perform the nearest neighbor search test. Okay, now today we will talk about the graph-based index structure here, the algorithm. I will detail it, the algorithm step by step. Okay, so when we consider your data set's scale, okay, if we are at the median scale, okay, only 10 to the 6, okay, we usually we can use this technique like the LSH or the tree structure or the graph-based structure. Okay, all these index structures can provide a very good accuracy, but some algorithms they will consume a lot of memory. If your memory is insufficient, maybe you have to consider to compress your data. Okay, there are some techniques that use the lookup table, use some consolidation technique, or you transform it into binary code and you compute the hanging distance. Okay, for this compressed data, okay, the accuracy is not good enough compared with this here, but the memory consumption is much less than this index structure. So it's also a trade-off. Okay, so depending on your equipment, if you want to be more accurate and your memory is large, you can choose these cards to do your next research. Otherwise, maybe you have to think about it. Okay, but it's for medium scale. But when we scale up to the billion scale, like the 10 to the 9, okay, you have 2 billion. So actually, all this method, even this method this index structure, they usually cannot all store in your memory. You have to think about other method. Okay, so you have to perform the space partition like k-means or PQ, or your data compression. You should use more to compress your data. Okay. So next we will consider the graph-based search. The graph-based search is one from here. You see there are 3 main categories of the index structure, and the current state of the art is graph-based search. It can achieve the highest accuracy and very fast, but its memory consumption is also very high. Okay, let me show you the detail. Okay, so graph-based is de facto a standard, and if all your data can be loaded on memory. So that's why in this talk I only consider the median scale, because at the billion scale, actually your graph structure cannot load in your computer, personal computer. I mean, you need a server level computer, at least more than 1,000 gigabytes memory. Okay, so If we consider only median scale, it's okay. Okay, so all the data can be loaded on memory, including the raw data and also the graph index structure data. It's fast and accurate. But if you want to scale the graph-based search to the billion scale, you have to think about alternative way. Okay, to simplify it or to use extra storage, like use some SSD, use SSD storage, because not all the data can be stored in memory. So maybe you have to think another storage like SSD to be your secondary storage, so that you can perform the billion scale search. Okay, so they think about some alternative way to this problem, to scale up to the billion scale data set. Okay, so first, this slide shows how to construct, but I will skip it. Okay, because suppose they already construct, you already construct a graph-based structure like this. Basically, you can think each node, each data is a node, each data point is a node. So you see here, 1, 2, 3, 4, 10, 11, 12. Okay, you have 15 data. Okay, so here each data is represented as a node, and there are some edge connections, means they are neighbors. Okay, so you see, if my neighbors, each node I have a neighbors connection. Okay, 1, 2, 3, 4, 5. So for this node, I have 5 neighbors. So these neighbors are close to me. So we can pre-construct. In our construction phase, I can calculate who are my neighbors and build the edge between them. But you see some. Also, for example, this node, and I will connect. I have 4 neighbors, so that I have 4 edges connect to them. But you see some edges are very, very low. You see, for example, this node to this node, they are too low, but they still have edge. So the idea is sometimes if you are visiting this node, and then you find your query is the wrong way. So there is a shortcut, so that you don't need to from your neighbors to here. You just follow the shortcut. So that's why they build. Sometimes they randomly choose some nodes between nodes. They build a shortcut, so that they can, in some cases, they can speed up the search. Okay, so this we will not detail the construction. Yeah. Okay, so I skip this. And okay, the most important is the search. How to perform the search. Okay, so here, you see, I already have a graph, and each node present a vector, a data point vector. Okay. So I give a query, a green point is our query. Alright, so from the graph you can see the closest, the nearest neighbor actually is point C, right? Alright, so let's follow the standard graph-based search. How can we give a query? How can we find the nearest neighbor? Okay, so first give a query vector, and then unfortunately, our start point is from here. It's our entry point. So it means each time your query will start from here. No matter where you locate, you just start from here. The point A. Okay, it goes far away, right? But the graph base is because we have a connection between our neighbors. So we can visit each point one by one. And we believe someday we will reach your nearest neighbor. to the query. Okay, so first we are at the entry point N. Okay, here is a you can think it's a queue, or the storage queue here. Okay, so the queue stores the closest point to the query. Okay, so because we start from here, so your first point is N, and the size is 3. This means we can store at most 3 points here. Okay, so here we start from N, and we can compute the distance to the query. Okay, suppose the distance to the query is 23. Okay, we make a record here in the queue. Okay, so then we start. Because your first entry is here, okay, so it's currently our best solution. It's this. And we pick this one to check its neighbors. Okay, you see the n's neighbors, check it and find its neighbors. So we find the 3 neighbors, I, N, and K. We find 3 its neighbors. Just follow the connection we already built here. Okay, so for these 3 points, J, K, and N, they are all the neighbors of N, right? So for these 3 points, I will compute the distance to the query. So for the J, the distance is 11. For K, the distance is 19, and the N, the distance is 15. Okay, so now I get the 3 other points and the distance, so I can update my queue. You see, the queue is updated, and we sort it according to the distance. Okay, because we can store only 3, at the most 3 points, so you have to remove 1. The N is removed. Okay, any problems? Okay, then we finish the first iteration. Okay, for the second, you just pick the first one. The smallest one is J. Okay, so if one J is now is the current best. Okay, then we check it. Okay, to find its neighbors. Okay, it contains many neighbors. For each neighbors, compute the distance to the query. Okay, so you see to compute all the queries with the query. And then based on this to update your queue again. Now you see the point B has the smallest distance. So you see we can very fast to traverse to a point very close to your query. Right? But we can keep only 3 candidates. Okay, so we remove the others. At the third iteration, okay, the current best is B here. Okay, we check B, and to see is the neighbors. Okay, these neighbors here, A, C, D. So again, we compute the distance, and we update our queue here. Okay, so you can find the best 3. Now it's updated like this. We are almost finished, and now your best. Always check your best in your queue. Okay, now C we check it, and we find some of them, and which ones. And because some points are already visited or checked, so we can skip the calculation, skip the distance calculation. Okay, and you see, and we see it's not updated. Okay, so but C is checked. We already checked its neighbors, and the relation to its neighbors, the relation to the query. Okay, so although the queue is not updated, but C is already checked, and the next to be checked is D, because D is not checked. Okay, so now we check D. D is here. Okay, so we check its neighbors and find the and finally all the Q, the three candidates are already checked, so we can start here and output the result point C and then the distance 0.5. Okay, so it's called a graph-based search. We finish it. I think it's very easy, right? Okay, some observations. Okay, I will skip it. So actually, you just compute how many the pathway you have to traverse to find your query, and also each time you have to compute the distance between your query and your neighbors. So it's your time complexity. Okay, you can actually find the time complexity is roughly equal to the length of your search path. Time is your average out degree. Out degree means how many neighbors you connect. So, okay, also the candidate size is also a problem. So if your candidate size is very small, always check only one candidate. In this case, you start from A and check B, and B you find, because you just check, at B you will check C and D, they are B's neighbors, but C is close to the query, so if my candidate, my Q is only keep 1, I will choose C and then remove D. Okay, so this will start in a local minimum. But if we can keep our candidate, our Q to be to keep more candidates, so you see C and D will they both keep, and then finally you find D can reach, its neighbors can reach and can be more closer to a query. Okay, so if you perform this, it's called a greedy search. But greedy search will always lead you to a local optimum, local minimum. So if we can keep more candidates, it's called a bin search. Bin is like you have a range. You will not just go through one direction. You will go many directions, like bin. Okay, so you can keep more candidates, and although it will take you more time, but your accuracy can be improved a lot. Okay, so there are some algorithms, pseudo codes. I will skip it. And here are introduce some basic graphs here. Okay, I also skip this. And some pruning algorithm, how to construct your graph. Your graph should not be very complicated, because if it's too complicated, your traverse on the graph will take much time. But if it's too simple, you may just find a local minimum. Okay, so actually it's also a trade-off. Okay, you have to think about your accuracy and the search time to make them balance. Okay, so that's a general idea. All the idea is from the hierarchical navigatable small word called HNSW. Okay, so now it's considered as a state of the art, a baseline. But if you want to perform the nearest neighbor search and use a graph-based index structure as a baseline, HNSW, and these ideas I already explained the basic idea. But this is a hierarchical structure here. So in hierarchical structure, this means in each layer, this layer is a complete all the data points in this layer. But if I will build a structure above it, I just randomly select some point to layer 1. From layer 0, I just randomly select some point in layer 1 and to build a graph. Okay, and also do again to build data points in layer 2. So when you do a search, okay, you can from layer 2 to 5 is neighbors. Okay, you just search search the nearest neighbors. Only use these 4 points. Which one are close to a query? And when you find this one is close to my query, and then I go to the final layer. The final layer contains the complete data points, so that I can find the correct answer. Okay, but it uses the hierarchical structure can make you search more efficient. Okay. It's called HMSW. You don't need to implement it. It's on just one line in the library. You just import the library, just one line, and set up your parameters. It will build a graph for you and also perform the nearest neighbor search for you. Okay, so it's a very famous HMSW. You must remember this method. All others are derived from this. Okay, this is our first topic. Okay, so next time